Okay, so firstly, thank you for coming this morning for a session. Okay, so today I want to introduce my research mainly about how to detect the method of detect the reproduce vulnerability, which is mainly made by the source code you reuse. Okay. No, doesn't work. No, I think this isn't you
Не
working out.
работает переключение. Это из-за второго экрана может быть. Ну, давай.
Oh, okay, I can do it. Oh, okay. So before I start my presentation, I want to talk about, self-introduce myself a little bit. So, okay. My name is Suka Nakajima, and I'm researcher at NTT Secure Platform Laboratory. And NTT is a company which is the largest ISP in Japan. And my main interest is vulnerability discovery and reverse engineering. And also, I am an organizer of Second CTF, which is the largest CTF in Japan. And I know that some of the Russian team participate in Second CTF. So I really want to say thank you about playing Second CTF. And also, I'm a founder of the CTF for Girls, which is the first security engineering committee for Japan. So that was my brief profile. And so firstly, I want to start from what is reproduce vulnerability? The answer is that reproduce vulnerability is a vulnerability which is copied to other source code or software from some reasons. Reproduce vulnerability is also called as a code clone vulnerability, but in this presentation, I will use the word reproduce vulnerability. So next, why this kind of thing happens? There's the three reasons why this kind of thing happens. The first is copy and paste. The second is source code sharing, such like sibling software like Firefox and Thunderbird. And third reason is fork projects, which is mainly happens in open source project. So this is the three reasons why it happens. So next, I want to talk about the risk of reproduce vulnerability. Sometimes the patch distribution date for reproduce vulnerability will be different. In past research, it says that patch release date differs like a maximum 118 days. If this kind of thing happens, it will be easy to attacker to analyze the patch and develop the exploit code for the patch one. So next, I want to talk about my research a little bit. And in the past research, there's a research called a redebug, which is a method which is based upon the source code. But however, like due to the method which is based on the source code method, it cannot be applied for the proprietary software products such as like Internet Explorer and Adobe Reader. Therefore, in my research, I will focus on the method which can detect reproduce vulnerability in the binary executables. So next, I want to talk about the previous research about method that targets binary executables. There's two main research, and the first one is a research called TEDM. And this research represents the assembly codes per basic blocks as expression, which means like tree structure. And this method uses tree edit distance to specify the reproduce vulnerability. And the next one research is called cross-architecture bug search in binary executables. And this research targets reproduce vulnerability which resides in the different architecture. And this research uses methods that calculates the basic block I/O based similarity calculation. However, this previous research cannot detect reproduce vulnerability when some type of source code modifications, such as like adding multiple lines of source code or change of the source code change, which changes the basic block IO. So, for my research, I target binary executables with even that sometimes a large source code modification happens. Okay. So next, I will talk about my approach of my research. The approach is simple. I just calculate the similarity between the assembly code by using a similar string search algorithm. First, I just collected the unpatched part of the vulnerability and calculated similarity between the target binary assembly. And the workflow for this approach have 3 steps. The first is the disassemble and normalization of assembly. And the second step is the similarity calculation between the assembly. And the third is the discrimination of the high, the similar part is whether a patched or unpatched part. So next, I want to talk about the details of my approach. The first step is the disassemble and normalization step, and in the disassemble step, it takes like 2 binary file. The first is the binary files which contains the unpatched vulnerability, and the second one is the target binary files, and just disassemble these 2 files. And next step, I want to talk about the normalization step. In some case, like different assembly, I mean operand will be generated even the source code is same. The right-hand side is an example of that. Oh, sorry. And this assemble has same source code, but when the compiler like changes, sometimes the operand will be changed. For the example, the memory address of call instruction changed, and also the register the changed in the original from the copy one. So therefore, in the normalization step, I normalize the operand, immediate value, and memory, and register to a string of val, mem, and reg. Yes. So next, I want to talk about the similarity calculation step. At the similarity calculation step, I used an algorithm called a Needleman-Boucher. Needleman-Boucher algorithm is like similar string search algorithm which is used in bioinformatics, like find a similar part in DNA. So using this algorithm, I applied halving gap penalty, which is also used as in the bioinformatics field. And this is kind of one of like score calculation mechanism in the Needleman-Boucher. So next, I want to talk about why I choose Needleman-Boucher algorithm. So in the bioinformatics fields, there's a lot of kind of similar string search algorithm, and especially like LCS and Smith-Waterman. But LCS is algorithm that search all similar part between 2 given string, which is also called like a global alignment algorithm. And Smith-Waterman is also called as a local alignment algorithm, which can search similar region between the 2 given string. And lastly, Needleman-Boucher is an algorithm that can search the region in the string to destination string that best matches the source string. It is also called semi-global alignment type of algorithm. Therefore, my research goal is to like find the reproduce vulnerability part in the target binary, file. Therefore, for that reason, the Nihon Bunshu was most suitable for my research. So next, I want to talk about the similarity calculation in this approach. Nihon Bunshu calculates a score given two strings, and this similarity calculation used that score. And just use the score of most similar part over the maximum score, which means that all matched case. So yeah, this is a similar calculation. And next, I want to talk about the score calculation method. I said, as before, I used the Affin gap penalty for the Nido and Bunshu. But before I explain about Affin gap penalty, I will talk about the normal gap one. For the normal gap penalty, it calculates the score like match and mismatch and gap case. I won't explain match and mismatch case, but for the gap case, it means that the compared string was not similar, but the adjacent, like next string, was matched. This is mean gap. So the Nindobon Bunshu's normal gap penalty, it calculates the match as a +2 point. For the mismatch, it will -2 point, and the gap, it will like -1 point. So next, for the Affin gap, it calculates at a match case, mismatch case, an open gap case, and extended gap case. The open gap means a gap that the first gap of the multiple gaps. And extended gap is a gap, the all gap except the open gap. And the score calculation would be for match, it will +2 point. And for mismatch, it will be -2 point. And for open gap, it will be -3 point. And extended gap, it will be like -0.5 points. So this point can be like set manually, but most of the case it use this score. Okay. So next, I want to explain about the formula of this algorithm. In this formula, I represent capital A as an patch part assembly and capital B as a target binary assembly. And after the formula calculates the score matrix X, Y, and Z. And after the calculating score matrix A, X, Y, and Z, the maximum point from score matrix X is used for the similarity calculation. So this is a simple example for this score formula. So you can see that the matrix X and Y and Z is calculated for this example, and the similarity calculation will use the maximum score in the matrix X. In this case, it will be like 4.5 point. And the similarity will calculate like 4.5 over 10. The 10 is calculated from the all match case means. And the result will be like 45%. Okay. So next, I want to talk about the advantage of the Affin gap penalty. The Affin gap penalty can mitigate the significant score drop due to the source code modification. For this example, like adding the one new line in the source code, it means that adding 8 new lines to the assembly code. So by using normal gap, it will be like a total 36 point. But by using the Affin gap penalty, it will be like total 37.5 points. So we can like mitigate a score drop for due to the source code modification. So next, I want to talk about how to discriminate the patched or unpatched. So this is very easy. I just first calculated the unpatched part assembly, the similarity of unpatched part assembly, and next I calculated a patch part assembly. And the case when the unpatched similarity of unpatched one was larger than patch part, I'll just extract it of the, for the candidate of the reproduced vulnerability. So next, I want to talk about the experiment I held. I held two experiment, and the first one is a goal for the evaluate the validity of my approach. And for this experiment, I used reproduced vulnerability, which was defined in past. The vulnerability is like CVE 2008-4314 and CVE 2008-5023. And I used this vulnerability and calculated the similarity between the original one and copied one. And after that, I calculated the similarity between the original one and dataset binary, which means the binary collected from Linux, which mean the binary which doesn't contains the reproduced vulnerability. Yes. So next, I want to talk about the vulnerability I used. The first one was CV 2008-4316, and this vulnerability originally was in the glib library, and it was copied in the software called Seahorse. And you can see that in the copied one, it deleted 2 lines from the original one. And the next case is like I used CV 2008-5023, and this vulnerability was original in the Firefox and copied in the software called SeaMonkey. And at the SeaMonkey, the 4 lines are deleted and 1 lines are modified from the original one. Okay, this is a result for the experiment. And for the result, my approach can detected reproduced vulnerability in binary executable. And also the similarity between the data set was maximum 9.7%. So maybe like over 20%, the similarity was over 20%, it might be like reproduced vulnerability. So next, I want to talk about the second experiment I held. The experiment I held is experiment which goal is to detect reproduced vulnerability from real-world software product. I collected 21 vulnerabilities, 14 from Windows OS and 7 from OpenSSL, and calculated similarity with the for the 1,000 binary files. And okay, this is a detail of the 14 vulnerability from Windows, and this is detail for 7 vulnerability from OpenSSL. And I mainly collected vulnerability which resides in the single function. So it's mainly like integer overflow and buffer overflow. Okay. And also, this is a detail of the binary files I collected. I collected mainly from latest Windows XP, Windows Vista 7, 8.1, Server 2003, and Server 2008. And also, I collected from VirusTotal, which was not detected as a malicious file. Okay, this is a result for this experiment. And for the result, I found 4 reproduced vulnerability candidate. And after I manual analysis, I found that the 2 was the real reproduced vulnerability, but 2 was not that code and no attack vector one. So this is detailed of the TV 2008 4520 case. This was a real reproduced buffer overflow vulnerability, and it was originally in the net API 32.dll, and it was copied to netlogon.dll. And the interesting thing is that this vulnerability was a vulnerability which used by the configure worm. And more an interesting thing is that this vulnerability's patch distribution date differs like maximum 3 months. As I said before, this vulnerability is used by the configure worm, so if the attacker realizes this reproduced vulnerability, the victim of the configure worm will be increased. So next, I want to talk about the CV 2011-0658 case. This vulnerability was originally in the OLE-AUT.dll and copied to OLE-Pro32.dll. But this vulnerability was not was data code, so the OLE Pro 32 used a technique called function forwarding. So if you call the vulnerable function in the OLE Pro 32.dll, it forwards the execution to the OLE AUT 32.dll. So it was dead code. So next, I want to talk about the CV 2015-1789 case. This vulnerability was originally in the libeay32.dll and is copied to the Junos Pulse VPN-BG.dll. And this DLL is used by the Windows Inbox Junos Pulse client, which is a VPN client, and maybe probably originally used by the Pulse client software. Yeah. And for this vulnerability, the Pulse Secure, which is a company which releases this Pulse client software, knew that they have a reproduced vulnerability, and they have a security advisory for this vulnerability, and it says that it was vulnerable. For this, this is the vulnerability fix state timeline for this vulnerability. And this vulnerability was originally fixed in the 2015 June. And the reproduced one, the Pulse Secure one, was fixed at 2015 August. So the fix date differs like 2 months apart. But also, I found this reproduced vulnerability in 2015 July. So I can easily write exploit code for the Pulse Secure one. So next, for last one, I will talk the details of TV 2015's 1793 vulnerability. And this vulnerability originally resides in libeay32.dll and copied to Junos Pulse VPN-BG.dll. Yeah, sure. But it also, the Pulse Secure writes the security advisory, and it says that this is not vulnerable because we don't use this code. So it means that it is like no attack vector to this vulnerability. So finally, I'll talk the conclusion and the future work of this research. For conclusion, I can say that my proposed method can detect reproduced vulnerability in the binary files, even there was a large source code modification. And by using my method, I found a real-world reproduced vulnerability. And for the future work, I'm now considering the method which can detect which can find whether the attack vector exists or not for the reproduced vulnerability candidate. And I'm now considering the method which can detect reproduced vulnerability which resides in multiple functions. Yes, so my presentation ends here. Thank you for listening. Spasiba. And do you have any questions or comments to my presentation?
Sorry, one question only. Okay. No question?
Did you try to use intermediate representation of code?
Sorry, pardon?
Did you use IR languages to perform?
Oh, okay. What language, programming language I use? You mean?
No. For example, OpenRail or
I just implemented by C++. Hmm? You mean
okay.
there?
Okay. Thank you.
Okay. Thank you.